are going to explain about the project entitled as a hybrid machine learning model for efficient XML parsing. Before getting into the video, let me give you a brief explanation. The project focuses on improving XML phrasing performance using a combination of traditional parsing methods and machine learning techniques. It intelligently predicts the most suitable phraser for different XML files, enhancing speed, accuracy, and scalability in data preprocessing. XML phrasing is a process of reading, interpreting, and extracting data from XML document so that it can be used by applications or programs. In simple terms, parsing means breaking down an XML file into a structure that a computer can easily understand and manipulate. There are two main types of XML parsers, DOM and SAX. DOM stands for Document Object Model and SAX stands for Simple API for XML. XML parsing is widely used in applications like web servers, configuration files, data exchange, and database communication to handle the structured data efficiently. Coming to the abstract states that a hybrid machine learning model for efficient XML parsing combining traditional parsing techniques with intelligent learning models. Unlike convolutional methods such as DOM and SAX, the proposed model uses supervised learning to predict XML structures and optimize phrasing performance. It improves speed, scalability, and memory efficiency while adapting the complex XML schemes. Experimental results shows that this hybrid approach significantly enhances processing accuracy and resource utilization, making it deal for real-time and large-scale data processing applications. Coming to the existing system. The existing system states that XML phrasing mainly depends on traditional methods such as DOM and SAX. The DOM phraser loads the entire XML documentation into memory and represents it as a historical tree structure and represent it as hierarchical tree structures, which allows easy data transversal and modification. However, this method becomes inefficient for large or complex XML files due to high memory usage and slow processing speed. On the other hand, the SAX parser uses an event-driven approach that treats the XML data sequentially and trigger events when specific tags are encountered. While SAX is more memory efficient, it lacks flexibility because it doesn't store the entire XML structure, making random access difficult. Both approaches face significant challenge when dealing with large-scale or dynamically structured XML datasets, leading to slower performance, high computational cost, and limited scalability. Moreover, these traditional parsers do not have any learning or adaptive capabilities, meaning they cannot optimize their behavior based on XML complexity. As a result, they are less effective in handling real-time or intelligent data processing environments, highlighting the need for a more efficient and adaptive XML-facing solutions. Coming to the proposed system or base paperwork. The proposed system introduced a hybrid machine learning model designed to make XML parsing faster, smarter, and more adaptable. Unlike traditional methods such as DOM and SAX that rely only on fixed algorithms, this system combines machine learning techniques with convolutional parsing approaches to intelligently analyze the process XML data. Using supervised learning algorithms, the model learns to identify and predict XML structures and tag patterns. This helps in optimize the phrasing flows, reduce redundant computations, and select the best phrasing strategies automatically. Essentially, the system combines the best of both worlds, the structural understanding of the DOM phaser and the efficiency of the SAX phaser. It dynamically chooses the most efficient parsing methods depending on the complexity and size of XML file. This hybrid approach results in faster parsing speed, lower memory usage, and better scalability, even for large and complex XML datasets. Over time, the model learns and improves, becoming more accurate with every new dataset it processes. Ultimately, the proposed system offers an intelligent, efficient, and scalable solution for XML phrasing, one that's ideal for real-time data processing, big data applications, and cloud-based environments. Coming to the dataset used in the project is a custom XML profiling dataset created by analyzing the performance of 5 XML facets, that is PXTG. It stands for XML facet. SAX stands for Simple API for XML. STAX stands for Streaming API for XML. DOM stands for Document Object Model. JDOM stands for Java Document Object Model on XML files of different sizes and structures. It contained key attributes such as file size, number of nodes, nesting depth, number of attributes, parsing time, and memory usage, along with a label indicating the best performing phaser for each file. These features help the machine learning models like ANN and SVM learn and predict which phaser is most efficient for a given XML file, thereby improving phaser speed and recognize and resource utilization. Coming to the novelty or extension or improvement or enhancement. This project enhanced traditional XML phrasing by introducing a machine learning based phaser recommendation system that predicts the most suitable XML phaser based on file structures and complexity. A stacked ensemble model combining random forest, XGBoost, and light GBM achieved 99% of accuracy, outperforming individual models. And a dynamic phaser code generator was developed to automatically create phaser implementation code based on the model prediction. This system supports real-time predictions and can be integrated into developer tools or IDs. To improve transparency, explainable AI, Line and Sharp was used for feature interpretation. A Flask-based web interface was built for users to input data and receive faster recommendations interactively. Coming to the flow of the work. Our project follows a systematic workflow that transforms XML profiling data into an intelligent faster recommendation system. Let's take a look at each step. First, we have data ingestion. The process begins with the creating of XML profiling dataset in CSV format. Synthetic XML profiling data is generated and stored in the directory dataset/XML phaser dataset.csv. This dataset is then loaded into a pandas data frame, which serves as the foundation for further pre-processing and model training. Next, data pre-processing. Before training, the dataset undergoes pre-processing to ensure data quality and consistency. We verified that there were no missing values. Next, all the categorical columns such as document type, memory constraint, and best phaser were label encoded into numerical form. Finally, numerical features were normalized using minimax scaler, bringing all values into 0 to 1 range for balanced model learning. Next, we have exploratory data analysis. To understand the dataset better, data visualization was performed. Bar graphs shown the distribution of phaser classes, pie charts illustrate how many XML elements were processed by each phaser type, and performance graphs highlights how different phaser perform under various processing priorities. Next, we have data splitting. The dataset is divided into 80% of training and 20% for testing using the test train split function. This ensures that our model can be evaluated properly and helps preventing overfitting during the training. Next, model training. 3 models were trained and compared. Firstly, support vector machine with tuned hyperparameters for classification and artificial neural network builds using the Keras sequential APIs with model weights using the model checkpoints. And finally, a stacked ensemble model that combines random forest, XGBoost, and light GBM using stacking classifier. This ensemble approach leverages the strengths of all individual models to achieve superior prediction accuracy. Then, model evaluation. Each model was evaluated using the metrics like accuracy, precision, recall, and F1 score. SVM has achieved 90.33% of accuracy, ANN achieved 89.08% accuracy, and the stacked model achieved at impressive 99.08% accuracy, making it the best performer. The bar chart was plotted using Matplotlib and Seaborn to visualize this comparison. And next, code generation feature. One of the key features of this project is a dynamic phaser code generator. Based on attributes such as file size, core count, depth, and destiny, the system automatically suggests the best phaser and even generates ready-to-use implementation code for phases like DOM, SAX, STAX, JDOM, and PXTG. This makes it highly practical for developers. Next, model deployment. Finally, the trained hybrid model was deployed using Flask web application. The front-end allows user to enter XML file characteristics, while the backend loads the trained model pre-processes the input, predicts the best phaser, and displays results instantly. This enables real-time predictions and make the system suitable for integration with developer tools or IDs. The algorithm used are artificial neural network, support vector machine, and a stacking classifier which combines multiple base models like LightGBM, XGBoost, and Random Forest. Coming to the requirements, we have hardware requirements and software requirements. Hardware requirements: operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements are application framework Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, and technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute this project, first we need to open the code folder, which contains the project source code files. The project code folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. In this, we have static folder. The static folder consists of files related to CSS, JavaScript, and Bootstrap files. Template folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb. This notebook.ipynb file is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the execution of the project, copy the path of the code folder from the address bar of the file explorer. Then, click on Anaconda prompt. Using the command cd followed by a space and then paste the copied path. This command is used to change the current directory of the code folder. Compile the app.py file using the command python space app.py in Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax error or logical issues. After running the app.py file, the Flask framework will be hosting the application locally at the default address. This is the address and this is a port number. Copy the local link provided by the framework and paste it into any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front-end built using Flask framework. So, this is a web page of the project displayed on the browser. In this page, we have Home button and Get Started button. Now, click on Get Started so that the login HTML page will be opened. Here, we need to give the details like username, full name, mail ID, mobile number, and password. Then click on Create an account so that all the given details are stored in signup.db and the login HTML will be opened, where we need to access the application by username and password. Then click on Sign In. The prediction page has been displayed. In this, we have prediction button, graph button, notebook button and logout button. Firstly, we need to click on prediction button. Here, you need to give the input to predict factors like PXTG, SAX, STAX, DOM, JDOM. Let me give you the inputs. File size 10.96. Element count 105609. Depth complexity is 41. Attribute density is 0.34. Required random access is no. Requires writing is no. Memory constraint is low. Processing speed priority is high. Document type will be a document. Then click on predict parser. The given inputs are pre-processed and the output will be displayed like your optimal XML parser recommendation is PXTG. The recommended parser name is given as PXTG and the confidence score is of 74.0% and the implementation code will be displayed here. You can copy the code or try any other prediction or download the results or share the results. Let me give you another prediction. Like the file size will be 3.49. The element count will be 355,852. The depth complexity is of 20 and the attribute density is 1.78. The required random access will be no and the required writing will be like no. The memory constraint will be high and the processing speed priority will be medium. The document type will be configure. Then click on predict parser. The given inputs are loaded and the output is predicted as STAX. The recommended parser is STAX and the confidence score is of 98.0% and the implemented code will be displayed here. You can copy the code or try any other prediction or download the results or share the results. Let me try another prediction. Like the file size will be 2.94 and the element count will be 199,192. Depth complexity is 49 and the attribute density is 4.82. Required random access will be no and the required writing is of yes. Memory constraint will be medium and processing speed priority is also medium. And the document type is of message. Then click on predict parser. The given inputs are loaded and the output has been displayed as SAX. The recommended parser is SAX and the confidence score is of 88.0%. The implemented code has been given here for SAX. You can copy the code or try any other prediction or download the results or share the results. Let me try another prediction. The file size will be 1.93. The element count will be 260,540. Depth complexity of 23. Attribute density will be 4.58. Require random access? No. Required writing? Yes. The memory constraint will be high. Processing speed priority is of medium. The document type will be data feed. Now click on predict parser. The inputs are loaded and the output is displayed as DOM. The required parser is DOM and the confidence score is of 87.0%. The implementation code has been given here. You can copy the code or try other prediction, download the results or share the results. Let me try another prediction. The file size is of 0.72. Element count will be 436,467. Depth complexity is of 31. Attribute density is 1.55. Required random access is yes. Required writing is no. Memory constraint is high. Processing speed priority is high. The document type will be of message. Now click on predict parser. The given inputs are loaded and the output is displayed. The output is displayed as JDOM. The recommended parser is JDOM. The confidence score is of 89.0%. The implementation of the code has been displayed here. You can copy the code or try out the prediction or download the results or share the results. Now click on graphs. Graphs are nothing but the data visualization. Data visualization means representing the data in graphical or visual format such as charts, graphs, maps or dashboards so that patterns, trends and insights can be easily understood. First graph we have is dataset different phaser class label graph. A dataset is a collection of data read by phaser, categorized by class labels and often represented using graphs. Second, we have profiling performance of different phaser on different file sizes. This graph shows how the speed or efficiency of different XML phaser changes as the file size increases. It helps compare which phaser performs best or slowdowns with larger files. Next, we have phaser with most number of tag processed graph. This graph shows which phaser can process the highest number of XML tags efficiently. It helps identifying the phaser that performs best in handling large or complex XML structure. Then we have accuracy graph. On the x-axis we have the algorithms and y-axis we have accuracy graph. Accuracy graph shows how correctly the model predicts overall outcomes. Next we have precision graph. In the precision graph, x-axis represent the algorithms and y-axis represent the precision score. Precision graph shows how many of the predicted positives are actually correct. Then we have recall graph. On the x-axis, it represents the algorithms. On y-axis, it represents the recall percentage. Recall graph shows how well the model identifies all actual positive cases. And we have F1 score graph. In F1 score graph, x-axis represents the algorithms and y-axis represents the percentage of F1 score. F1 score graph shows the balance between precision and recall in the model performance. And finally, we have explainable shape graph. XAI shape graph is a visualization used in explainable AI to show how each feature influences a model predictions using SHAP. It helps you see which features are important and whether they increase or decrease the predicted outcome. Then click on Logout. This is all about the project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.